Welcome back. Let's learn about continuity of multivariable functions. Alright, so far you've been introduced to multivariable functions and how to find their limits, but now we're going to take a look at continuity of multivariable functions. In Calculus 1, for single variable functions, we learned that if a function is continuous, that means its graph has no interruptions of any kind. No jumps, no holes, no gaps, just a continuous curve with no breaks in it. And those same ideas apply to multivariable functions as well, it's just that it's extended to more dimensions. Alright, now in Calculus 1, for a single variable function, what we would do is determine the interval or intervals where that single variable function is continuous. And these intervals were in one dimension, right? They just account for the one independent variable, that typically being x. And so for example, with this graph right here, for the single variable function f of x, you can see that the function is continuous except right here at this vertical asymptote, which would be where x is equal to 0. So we would say that this function is continuous everywhere except at x equals 0. Or the way that we would typically express that is to say that the function f of x is continuous on the open interval from negative infinity to 0, unioned with the open interval from 0 to positive infinity. Alright, these are the intervals of continuity for this function f of x. It just accounts for the values of x for which the function is continuous. Alright, and these intervals are in one dimension. You could represent it like this by drawing an x-axis and including all the values of x except where x equals 0. So you draw an open point at 0 to indicate that. Alright, so clearly when we're talking about continuity of single variable functions and we're looking at intervals, we're just talking about one dimension. We only have to consider the values of x for which the function is continuous. But for multivariable functions, such as with functions of two independent variables, there is more to consider because there is more than one independent variable. And so for a function such as f of xy, where the independent variables are x and y, we would have to consider all the ordered pairs or all the points of xy in the xy plane where the function might be continuous. But what do we actually call those groupings of points for x and y where the function is continuous, right? What would we say that a multivariable function is continuous on? Well, since we're working with more than one independent variable, we're not going to refer to these areas of points where the function is continuous as intervals anymore, because the intervals that we used for single variable functions were for one independent variable. And so we don't really work with intervals anymore for multivariable functions. Instead, we work with what are called regions, specifically regions in a plane, or more simply just plane regions. Okay, for the continuity of functions of two independent variables, we will consider points in what we call plane regions, which are just sections or regions within the xy plane that represents a collection of points. Okay, by considering these regions, we are accounting for both of the independent variables, that being x and y. Okay, just like with single variable functions, where the intervals only dealt with values of x, so we would just consider the x-axis for those intervals. For multivariable functions, we need to consider the values of both x and y, so we use both of those axes, which together form a plane, and so a collection of different values of x and y, or different points where a multivariable function is continuous, would form a two-dimensional region. Okay, and we typically denote or refer to these regions with the letter capital R, just as you see right here. And for these regions, we can consider two different types of points. First up, we have interior points, which are points inside the region R. So for example, in this region here, a point right here would be an interior point. Alright, that point lies inside of the region. And then the other type of point that we could have are called boundary points, which are points along the outside of the region R. So for example, a point right here along the outside of the region would be a boundary point. Okay, really the way you could think about the difference between these two types of points, if it's not already obvious, is if you were just to look around that point, if there are points around the point that are not inside the region, in this case, I'm talking about the points out here. If there are points around that specific point that are not in that region, then that point has to be a boundary point. It must be along the outside or the boundary of the region. And so if you were to do the same thing for the interior point, if you were to look at points around that point, you can see that all around that point are other points inside the region, so that is clearly an interior point. Okay, and the idea of these interior and boundary points are not all that unfamiliar to us. It's just like when we work with intervals for single variable functions, typically we have endpoints as well as interior points, which are any points between the endpoints of an interval. All right, you probably haven't heard them called interior points a whole lot, but that is what we would call them, and that's the same idea here. And by considering these two different types of points for plane regions, we can classify the type of region we're working with. What I mean by that is that if every point in a region is an interior point, meaning there are no boundary points, if that is the case, then we would call that region an open region. All right, just like for intervals, if there are no endpoints, then you have an open interval. For example, the interval from -infinity to infinity. There are no endpoints for that interval. That's an open interval. We're working with the same concept here. If there are no boundary points and every point in a region is an interior point, then the region is open. Okay, and then on the flip side, if a region contains all its boundary points, meaning it has boundary points all the way around it, and all those points are defined, then the region is a closed region. Okay, the region would be limited to the points inside the region bounded by those boundary points. And then if a region does not contain all of its boundary points, meaning that it's not entirely enclosed, maybe it's enclosed on one side, but then extends forever in another direction, or maybe it's not defined at all the different boundary points for a particular scenario, then you wouldn't call that region open or closed. Okay? But now when we are talking about the continuity of functions of two independent variables, we are looking to see if that function is continuous for all possible points xy in the open region R that is the entire xy plane. All right, so imagine a region that covers the entire xy plane infinitely in all directions. That is the open region that we consider for functions of two variables. We want to look at all the different points within that region and determine what points in that region is the function continuous for. Just like for single variable functions where we consider what values of x on the open interval from -infinity to +infinity would that function be continuous for. All right, but what does it mean for a function of two independent variables to be continuous at a point? Well, let's take a look. Remember from Calculus 1 that for single variable functions, a function f of x is continuous at a value of x equals x sub 0, on an open interval I if the following three things are true. The function had to be defined at that value of x, so f of x sub 0 is defined. The limit as x approaches that value of x sub 0 on the function, needed to exist, and then that limit as x approaches x sub 0 of the function needed to be equal to the actual value of the function at that point. All right, so really this third condition is the most important because if this one is true, then the other two are true as well. All right, because in order for the limit as x approaches some value on the function to be equal to the actual value on the function, that limit has to exist and this value has to be defined. Okay, so that kind of takes care of those first two conditions. This is the highlight here. We would say that a function is continuous at a value of x if the limit at that value on the function is equal to the actual value on the function at that value of x. And we can extend this definition of continuity to functions of two variables. A multivariable function, f of xy, is continuous at a point x sub 0, y sub 0 in an open region R if the following three conditions are met. The first being that the function is actually defined at that point x sub 0, y sub 0. The second being that the limit as x and y approach that point on the function actually exists. And then the third being that that limit is equal to the actual value on the function. All right, so once again, the third condition here is really the most important one because in order for this to be true, the limit does have to exist and this value on the function does have to be defined. All right, and so if those two things are true and they're equal, then the function f of xy is continuous at that particular point x sub 0, y sub 0 in an open region R. Okay, so not an entirely new concept. We're just taking something from Calculus 1 and extending it into another dimension. But a couple notes here, some things to know about continuity of a function of two variables. Firstly, the function f of xy is continuous in the open region R if it is continuous at every point in that region R. All right, in other words, if a multivariable function is continuous for every single point in the xy plane, then we would say that it's continuous everywhere. This is the equivalent of a single variable function being continuous on the open interval -infinity to +infinity. All right, if there are no discontinuities for a multivariable function f of xy, it is continuous everywhere. Or a more simple way to view continuity for these multivariable functions is that a function is continuous at any point in the region for which it is defined. Essentially, what that means is you're just looking at the domain of that function. The domain tells us where the multivariable function is defined, and that also happens to be where the function is continuous. Now, there are some exceptions to that if you're working with piecewise functions, but generally what this means is that if you want to find the region for which a multivariable function is continuous, you just have to find its domain, which is something that we have already done previously in Calculus 3. Okay, so keep that in mind, but then one more point here. All the continuity properties that you are familiar with for single variable functions also apply to multivariable functions. So this includes things such as the fact that polynomial functions are continuous everywhere, they have no discontinuities. It also includes that rational functions, or functions that look like fractions, they are continuous everywhere, that the denominator is not zero. And it also includes that continuity holds for composite functions. All right, and I'll show you some examples of this in just a bit, but if you form a composite function where you're plugging a multivariable function into a single variable function, and both of them are continuous, then that composite function will also be continuous. All right, again, you'll see an example of that in just a little bit, but those are all the extra notes I wanted to cover regarding continuity of functions of two variables. And so now that you're familiar with the big ideas of continuity of functions of two variables, let's look at a couple examples where we determine the continuity of some multivariable functions. First up, we have this function, f of xy is equal to 2x³ plus xy plus 4y. All right, so if we want to determine the continuity of this multivariable function, we have to ask ourselves, are there any points xy for which this function would be discontinuous? In other words, are there any points that would cause an issue for this function? Just think of it like determining the domain. Are there any values for which the function would be undefined? And in this case, the answer to that question is no, right? This is a polynomial expression. It just deals with terms of different powers of x and y. And polynomial functions are continuous everywhere. It doesn't matter if it's a single variable function or a multivariable function. If you have a polynomial, that function is continuous everywhere. All right, so that would be my final answer here. But if you actually want to write out the points of x and y where it is continuous, then you could express that the same way that we write the domain of multivariable functions. All right, so in this case, the function would be continuous on the set of x and y values such that x and y belong to R squared, or the set of all ordered pairs of real numbers, which does mean the same thing as the open region R that would be the xy plane. Okay, if you're not familiar with this notation, be sure to go back and watch the lesson on the intro to multivariable functions. All right, but this would be the final answer. That is where this function is continuous. Let's take a look at another function. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. This time our function is f of xy is equal to 1 divided by the square root of x² plus y². All right, so once again, if you want to determine the continuity of this function, you want to ask yourself, are there any points of xy for which the function would have a discontinuity or where it might be undefined? And in this case, we do have a rational function, so the denominator cannot be 0. A rational function will be continuous everywhere that the denominator is not 0. And in this case, the denominator would be 0 when x and y are are 0, right? If you set that denominator equal to 0, the only way that it will be equal to 0 is if both x and y are 0. All right, you have x squared plus y squared, so anything else you plug in there is getting squared and added together, so that will never be 0 unless x and y are 0. And also notice that we don't have to worry about any negative values being underneath the square root because x squared plus y squared is always positive. All right, so in this case, we would say that this function is continuous on the set of xy values such that xy does not equal the point 0, 0. That would be my final answer here. Okay, let's take a look at another function. This time our function is f of xy is equal to the square root of y times e to the power of y divided by x. All right, so looking at this function, are there any potential values of x or y that would result in some kind of discontinuity? Is there a way that this function would be undefined? Well, for one thing, we have the square root of y right here, and you can't take the square root of a negative value. So we know for this part right here that y should be greater than or equal to 0. That's definitely a restriction we have here for this function in order for it to be continuous. And then we also have this fraction as the power of e, and that denominator cannot be 0. All right, so the value of x there cannot be 0. So these are our two restrictions. X cannot be equal to 0, and y needs to be positive, or greater than or equal to 0. And those are the only restrictions. Any other values of x and y will be just fine for this function. All right, so we would say that this function is continuous on the set of xy values such that x is not equal to 0 and y is greater than or equal to 0. Okay, that would be the answer to this example. And so hopefully now you get the idea from these last three examples that determining continuity of multivariable functions is very similar to finding their domain. All right, so we'll look at more examples of this in the examples video for this topic, but now what I want to do is take a look at some examples where we consider some composite functions. Starting with this example, we want to discuss the continuity of the composite function h of xy, which is equal to g of f of xy, where f of xy is a multivariable function, f of xy is equal to x squared plus 2xy, and g is a single variable function, g of t. G of t is equal to t times sine t. All right, so to determine the continuity of this composite function, we have a couple options here. We could straight up write out the composite function. We could plug f of xy into g of t, and then determine the continuity of that composite function, which would be a multivariable function. Or what you can do is make use of the fact that continuity holds for composite functions. What I mean by that is if you take a look at these two functions we have here, both of them are continuous, right? F of xy is a polynomial function, so that will be continuous everywhere. There are no discontinuities. And g of t is equal to t times sine t. T is a function that is continuous everywhere, and so is sine t. Both of those two functions are continuous everywhere, so multiplying them by each other to form g of t is also a continuous single variable function. So both of these functions are continuous, so if you plug the multivariable function into the single variable function to form a composite function, that composite function will also be continuous. The continuity will hold. All right, so this function is continuous, and so is this function. Both of them are continuous, so h of xy is continuous everywhere. All right, that would be the final answer to this example. If you wanted to, you could write out the actual function h of xy. Like I said, you could plug x squared plus 2xy into g of t. You'd plug it in here for this t and here for this t, but that's unnecessary work that we don't have to do here. All right, let's take a look at another example like this. Here we once again want to discuss the continuity of the composite function h of xy is equal to g of f of xy. This time our multivariable function f of xy is equal to x minus 3y plus 1. And then the single variable function g of t is equal to 1 divided by t. All right, now to determine the continuity of this composite function, we should look at what is the continuity of each of these two functions that will make up that composite function. Starting with the multivariable function, f of xy is just a polynomial function, so this function would be continuous everywhere. So I'll just write down that it is continuous. There are no discontinuities for that function. But what about g of t? g of t is equal to 1 divided by t, that is a rational function, and so the denominator cannot be 0. All right, so in this case, t cannot be equal to 0. And so if we were going to form this composite function, we would be plugging this expression for f of xy into t for the single variable function. So if t cannot be equal to 0, and we would be plugging this expression in for t to form h of xy, then for that composite function, this expression could not be equal to 0. All right, what we find here is that x minus 3y plus 1 cannot be equal to 0. Okay, and you would find that if you were to set up h of xy, if you actually plug this in to g of t, you would have 1 divided by that expression, so it could not be equal to 0. All right, and so that's pretty much it. We would say that h of xy is continuous on the set of values for x and y such that x minus 3y plus 1 does not equal 0. All other points would be points where this function is continuous. So that is the final answer to this example. All right, so that should give you a good taste of what it's like to determine continuity of multivariable functions, including composite functions. But now I want to take a closer look at something we really haven't talked about yet, which are the points where a function is discontinuous. Because similar to Calculus 1, with single variable functions, points where f of xy, a function of two variables, is not continuous can be classified as either removable or non-removable. All right, there are both removable and non-removable discontinuities for multivariable functions. And here's the difference between those two types of discontinuities. The way we look at it is that if a point is not defined on that function and the limit at that point does not exist, then the discontinuity is non-removable. All right, so a function would be discontinuous at a point where it's not defined, but if it's also the case that the limit doesn't exist at that point, then we would classify that discontinuity as non-removable. All right, now on the other hand, if a point is not defined on f of xy, but the limit at that point exists, it is removable. What you could do is define f of xy as being equal to its limit at that point. All right, so in both cases, the function is not defined at the point in question where we have a discontinuity, but the difference is that if the limit does not exist, it's non-removable, but if the limit does exist, then it's removable. And this should make sense if you think back to Calculus 1, when we first talked about removable and non-removable discontinuities. Functions that had removable discontinuities would look something like this. You'd have what looks like to be a continuous function, but somewhere along the function would be a point where it's not defined. We call that discontinuity removable because even though the function is not defined there, the limit at that point exists, right? The limit from the right side leads to this value of y, and the limit from the left side also leads to that same value. So since that limit exists, this is a removable discontinuity. You could remove it by redefining f of x to have this particular y value for this particular x value. All right, typically what this would look like when you were working with single variable functions is you would have a rational function where you can manipulate it in some way such that some factors cancel out and it no longer has that discontinuity where the denominator is 0 because you essentially rewrote the function in such a way that that discontinuity is gone. All right, as a quick example, x squared minus 4 divided by x plus 2, you could factor that numerator since it's a difference of squares, and you'd have x plus 2 times x minus 2. So in this form, there's a discontinuity at x equals negative 2 because that would make the denominator 0. But by rewriting the function in this way, these two factors cancel out, and now you've rewritten the function as just x minus 2, which would be continuous at x equals negative 2. So we would call that a removable discontinuity. Okay, but formally the way that we define that is if a function is undefined at a point, but the limit at that point exists, then it's removable. But if a discontinuity is non-removable, then that means that the limit does not exist for that point or for that value of x in this case, right? And you can see that here. From the right side, as you approach this value of x, you're leading to this value of y, but from the left side, as you approach that value of x, you're leading to a different value of y. So the limit does not exist here, so the discontinuity at this value of x is non-removable. Okay, the same idea is going to apply for multivariable functions. If a function is not defined at a point, it does have a discontinuity, but if you were to look at the limit at that point, you can determine whether it's non-removable or removable. If the limit does not exist, it's non-removable, but if it does exist, it's removable. All right, so as an example, consider this function, f of xy is equal to x to the power 4 plus y to the power 4 divided by x squared plus y squared. We actually looked at the limit of this function in a previous lesson, specifically the lesson on limits of functions of two variables, and we were able to show that the limit as xy approaches 0, 0 on this function exists. Particularly, that work looked like this. We used polar coordinates, but that's totally valid. We were able to rewrite the limit using polar coordinates and found that the limit was 0 as xy approaches 0, 0. But as you'll notice, this function is not defined at that point 0, 0, right? If you plug in 0 for x and y in this expression, you will get a denominator of 0. So this function is not defined at 0, 0, but the limit at 0, 0 does exist. This is an example of a removable discontinuity for a multivariable function. This function is not continuous at that point, but since the limit exists at that point, you could remove that discontinuity. And in this case, there's nothing we can cancel out within the function to show that that discontinuity is removable. Instead, what we can do is redefine the function like this. We'll have f of xy is equal to a piecewise function where you have x to the power 4 plus y to the power 4 divided by x squared plus y squared for points xy not equal to 0, 0. And then you'll just take whatever the limit is equal to at that point and say that the function is equal to 0 when x and y are equal to 0, 0. All right, you can redefine the function in this way, and now you have removed that discontinuity. Okay, and I didn't write it down, so I'll do it now, but the point 0, 0 is a removable discontinuity. All right, so that is what we have found here. Now, if we were to look at a different function, let's say we're looking at the function f of xy is equal to x squared minus y squared divided by x squared plus y squared, this function also has a discontinuity at 0, 0. When x and y are both 0, this denominator will be 0, and so the function would be undefined and therefore not continuous. So the function is undefined at 0, 0, but does the limit exist? Well, let's take a look at it. We know how to determine the limit of a multivariable function, so let's set it up. We'll have the limit as xy approaches 0, 0 of x squared minus y squared divided by x squared plus y squared. Now, if you were to plug in 0 and 0 for x and y, you will get an indeterminate form of 0 divided by 0. So it is most likely the case that this limit will not exist. You would want to show that there are two paths that lead to different values of z. But I'm going to use a little trick here. I'm going to make use of polar coordinates again. If we rewrite this limit in terms of polar coordinates, we would rewrite it like this. You'd have the limit as r approaches 0 from the right of that function, but x squared plus y squared we know is equal to r squared, so we'll have r squared in the denominator, and then we have to replace x and y with what they would be equal to in terms of polar coordinates. Remember that x is equal to r cosine theta, and y is equal to r sine theta. All right, so plugging those in for x and y, you'd get r squared times cosine squared theta minus r squared times sine squared theta. All right, and then these two terms and the denominator have a common factor of r squared. So we could cancel that out here, and what you'd be left with is the limit as r approaches 0 from the right of cosine squared theta minus sine squared theta. And what do you notice about this limit? Well, there's no r's, right? There's no r's left. So technically what we're looking at here is just a constant value, at least with respect to r. So the limit here would just be equal to cosine squared theta minus sine squared theta. But what is that, right? That doesn't really look like a value of z that our function leads to as it approaches 0, 0. What is going on here? Well, what this is saying is that the result of this limit depends on the value of theta. It depends on the angle. So the limit doesn't exist here, because depending on the angle or the direction from which you approach the point, this value will be different. The limit will approach different values of z. That's what this means. So the limit here does not exist. All right, I didn't really talk about this in the lesson video on limits of multivariable functions, and that's because usually when you show that a limit does not exist, you use that other method of actually finding two paths that lead to different values, but this is also a way that you could do it. I really only showed you examples in the past where using polar coordinates resulted in an actual value, typically 0, but this can happen too. You can show that a limit does not exist using polar coordinates. But putting that aside, what this means is that this function is not only undefined at this point, but the limit at that point also does not exist. So this is not a removable discontinuity. Unlike the previous example, the discontinuity at 0, 0 is non-removable for this function. All right, so my final answer here would be since f of xy is undefined at that point 0, 0, and the limit does not exist, the discontinuity is non-removable. All right, that's how we would classify the discontinuity for this function. So if you're given a function and you need to determine if a discontinuity is removable or non-removable, all you have to do is first check to make sure that the function is undefined at that point, and then see if the limit at that point exists or does not exist. If it does, the discontinuity is removable, but if it does not, then it's non-removable. And so that's all I wanted to talk about regarding continuity of a function of two variables. But real quick, to close out this lesson, we can also consider the continuity of multivariable functions of three variables. And it's really not all that different from what we've already done with single variable functions and functions of two independent variables. The continuity of a function of three variables works like this. A function f of xyz is continuous at a point x sub 0, y sub 0, z sub 0 in an open region R if the following three conditions are met. And by the way, this region would now be a three-dimensional region because the function itself would represent a four-dimensional shape. So just like how its domain would be in 3 dimensions, so would the open region R that we're considering here. All right, but anyway, the three conditions should look pretty familiar. The first one says that the function needs to be defined at that point x sub 0, y sub 0, z sub 0. Secondly, the limit at that point needs to exist on the function. And then thirdly, that limit needs to be equal to the value on the function. Once again, that third condition is really all that matters here, because if this limit is equal to the value on the function, then that limit exists and the function is defined at that point. Okay, and the bottom line here for continuity, just like with our other functions, these functions will be continuous at any point on the region for which it is defined. So really, you're just looking at the domain of these functions of three variables if you want to determine where they're continuous. Okay, obviously, if you're asked to determine if it's continuous at a specific point, then you would want to check these conditions. But in general, if you're just looking for the overall continuity, just find the domain. And so to end this lesson, let's just take a look at two quick examples. Okay, so here we have two functions of three independent variables, and for both of them we want to determine where they are continuous. Starting with the first one here, f of xyz is equal to x squared times y squared times z squared. That is a polynomial, right? That's going to be continuous everywhere. You could plug in anything you'd like for x, y, and z, and you will get a defined value. So this function is continuous everywhere. Okay, and that's really all you need to write down. You could write down the set of all values of x, y, and z, such that all those points belong to R cubed, or the set of all ordered triples of real numbers, but that's sort of unnecessary because that's what's implied by saying that this function is continuous everywhere. All right, but then if we look at this other function here, f of xyz is equal to x plus y plus z divided by x squared plus y squared plus z squared minus 6. Just like with any other rational function, that denominator can't be 0, so if it is equal to 0, that would be a point where the function is not continuous. So in this case, x squared plus y squared plus z squared minus 6 cannot be equal to 0, which means that this function is continuous on the set of all values x, y, z, such that x squared plus y squared plus z squared minus 6 does not equal 0. All right, that is where that function is continuous. And so with that is all I had for this lesson. But if you want to get some more practice working with continuity of multivariable functions, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.